if you are doing experiments and showing your experimental results to the outside world, your audience will accept the results only if they are convinced that you have taken sufficient care in conducting the experiments. The same idea is applicable to numerical simulations as well. The computational fluid dynamics simulations that we conduct when we go outside and try to convince the audience that our results are of high quality, we have to first see the order of accuracy of the numerical schemes that we are using. So far in our discussion, the schemes that we have defined, we have very little control over the accuracy of those schemes. So in this lecture, we'll see how we can improve the order of accuracy of our schemes. Recall the definitions of numerical derivatives of the function u of x. We have defined the derivative in three different ways. First one is forward difference that involves the values of u at I and I plus 1. Then there is backward difference that includes I and I minus 1 points. And third is central difference that has I plus 1 and I minus 1 points. Both forward and backward differences are first order accurate, while central difference is second order accurate. Now let's say, just for fun, we want to create u prime I in terms of ui plus 1 and ui plus 2. How can we do so? We use Taylor series and we expand ui plus 1 from ui plus delta x ui prime plus delta x square by 2 ui double prime plus delta x cube by 6 ui triple prime, etc. And similarly, we can write ui plus 2 equals ui plus twice delta x ui prime plus twice delta x whole square by 2 ui double prime plus twice delta x whole cube by 6 ui triple prime, etc. So now our goal is to find the constants a, b, c and p such that ui prime equals aui plus bui plus 1 plus cui plus 2 plus order of delta x to the power p. The purpose of this exercise will be clear very soon, but let's first do this exercise. Having set our goal to find the constants a, b, c and p, we write aui plus bui plus 1 plus cui plus 2 equals aui plus b multiplied by ui plus 1, that ui plus 1 we take it from the Taylor series expansion. Then again we add c ui plus 2, I plus 2 we take it from the Taylor series expansion of ui plus 2. Finally, we add all the terms. In a way, we take ui prime, etc. together. So we have a plus b plus c ui, then b plus twice c delta x ui prime plus b plus 4c delta x square by 2 ui double prime plus b plus 8c delta x cube by 6 ui triple prime, etc. Our goal now is to select a, b, c in such a way that a plus b plus c equals 0, b plus 2c multiplied by delta x equals 1, b plus 4c multiply x by delta x square by 2 equals 0. If I solve these three equations, I get the values of a, b and c as a equals minus 3 by twice delta x, b equals 2 by delta x, and c equals minus 1 by twice delta x. Although it is not absolutely necessary, but we can check b plus 8c, that is minus 2 by delta x. Why we are taking b plus 8c, it will be clear very soon. We now see with those a, b and c values, we can express ui prime equals minus 3 by twice delta x ui plus 2 by delta x ui plus 1 minus 1 by 2 delta x ui plus 2 and plus we have of the order of delta x square. Why delta x square? Because b plus 8c is minus 2 by delta x. So b plus 8c multiplied by delta x cube by 6 will give us delta x square by 3 exactly. And these are additional terms, part of truncation errors that will remain in our scheme. And the leading term of truncation error has this delta x square. So the usefulness of b plus 8c calculation is clear now. If b plus 8c becomes 0, then of course our scheme will be at least third order accurate, but that is not happening. Since b plus 8c is 2 by delta x, then our scheme is second order accurate here. That means our ui prime is minus 3ui plus 4ui plus 1 minus ui plus 2 divided by twice delta x, and this scheme is second order accurate. So we have a derivative of u prime that is second order accurate. You may wonder that we already had central difference, that is a second order accurate derivative. But with this exercise, we have accomplished two things. First is, you see that this is not a central difference expression. This is forward difference. Earlier we had forward difference which were based on ui plus 1 and ui only, and that was only first order accurate. Now we see that we can create forward difference with ui plus 1 and ui plus 2, and we can have second order accurate scheme. So we have a forward difference scheme with second order accuracy, which we didn't have before. The utility of such schemes I'll show you in upcoming lectures, but right now we see that we can have forward difference scheme with second order accuracy. These are called 3-point forward difference, since we are using 3 points I plus 1 and I plus 2. So this 3-point forward difference idea, you can now take it forward and apply it to backward difference as well. So you can try to create a numerical scheme based on I minus 1 and I minus 2. And if you do so, you will see that it is possible to have a second order backward difference. And similarly, you can have more and more terms. So you can have 4-point forward difference or backward difference schemes, and that way you may achieve a third order forward difference or backward differences. And such higher order numerical schemes you will probably use in future if you do master's level or PhD level research in computational fluid dynamics. So that's all for this lecture. Thank you. I'll see you in next class.